start recording. There we are. Qualitative analysis. So we are analyzing things. No worries. So in terms of, did you get the answer key? Oh, I have an answer key. I will make an answer key. Okay, yeah. What was I saying? Oh yeah, in a titration, we analyzed things, but we analyzed it using numbers. So that was a quantitative analysis. We figured out the concentration. Here, we're just saying what is present, not how much, just which ions are present. So we're analyzing a solution, and it contains maybe ion A, ion B, ion C, but we don't know which of those. It might contain A, it might contain just B, it might contain C and A, or all three, we don't know. And we're going to do this by a method called selective precipitation. And selective precipitation is where we precipitate out the ions one at a time. Do you guys know what I mean when I say precipitate out?
I guess.
Yep.
Is it like less of see if they're not soluble, so you can do it with times there?
Yeah, basically you find something that it will not, that it will be solid with. Okay, so you make a solid. Okay, so we precipitate out the ions one at a time. So we have a beaker here in our first example. And it contains either calcium nitrate or lead nitrate or both. Now, when we say Ca, calcium nitrate, what do we really mean? Ca2+. And when we say lead nitrate, PbNO3 2, what do we really mean? Pb2+. Or we might have both. Why am I ignoring the nitrate? Because nitrates are soluble with everything, and that means that those nitrates are just spectator ions. Okay? And if you're like, hey, how do I know? Nitrate is soluble with everything. Where could you look? You could look on your data booklet. Please make sure you have your data booklet out. If you do not have a data booklet, but you know you have it at home, you can come borrow one of the white ones. If you believe you have lost the data booklet, you can come and get a new pink one from this shelf right here. Now, the key thing here is that we want to precipitate either calcium or lead, because we want to precipitate them out one at a time. If I add something that precipitates both of them, will I know whether I had calcium or lead? No, I'll be like, well, I've got maybe one of them, or maybe I have the other, or maybe I have both. So if you add something that precipitates both, then that will not work. What if you add something that precipitates neither of them? Nothing's going to happen, right? So you need something that will form a solid with either calcium or lead, but not both. So let's look on our data booklet and find an anion that will precipitate calcium or lead, but not both. When you found one, tell your partner what you think you've got. Jonathan, come sit over with Aaron. Be friendly. Yeah.
Yeah.
So can we choose nitrate? Does nitrate work? No, nitrate is soluble with everything. How about chloride? Does chloride work?
Yeah.
Yes, because chloride will precipitate lead, but not calcium. Remember, if it's low solubility, that means we have a solid, which means that is our precipitate. If you find the word precipitate difficult, you can always just say PPT. Okay? How about sulfate? Would sulfate work? Why does sulfate not work? It precipitates both the calcium and the lead, so that will not work. How about sulfide? Sulfide will work because calcium will not precipitate, and lead is down in the all others category. Okay, so you could use sulfide or chloride or bromide or iodide. How about hydroxide? No, because calcium and lead both fall down here. And how about phosphate, carbonate, sulfate? No, again, calcium and lead would both precipitate. So you couldn't tell the difference between them if you used that. Okay, so let's go back here. And so we could use either sulfide or chloride, or there's a couple others listed with chloride. There's bromide and iodide. Do you guys have a preference? Chloride. Chloride's always an easy one, right? Is it possible to add chloride ions all by themselves? Can you go into the back room and get me a jar of chloride ions? No. Why not? That would be chlorine. That would be neutral chlorine, as opposed to chloride, which is negative. Right? Chloride has a full shell because it gained an extra electron, whereas chlorine shares an electron with its buddy, and that's how it gets that extra electron. That's neutral chlorine. Why can I not just get chloride by itself? What would chloride ions do to other chloride ions? They would repel. Yes? You cannot get negative ions by themselves. What do they always have to partner up with? They always have to partner up with a positive ion so that you have a stable positive, negative arrangement. Okay, so we're going to pair up our ion with a partner, and because we have a negative ion, we need to pair it with a positive ion. Now we're adding this to our reaction mixture. We want a partner, we want that positive ion to not react with anybody else because we don't want to complicate things. We don't want to be like, oops, I added strontium and that's going to react with something in the future. That could be a problem. Try and find a positive ion that is unreactive. So go to your data sheet, find an unreactive positive ion. In terms of solubility, unreactive, does that mean it's going to be a soluble compound or a low solubility compound? Soluble. It means it should be soluble because it means you will not form a precipitate. I don't want this ion to be added to the mixture and cause some extra precipitate to form. Because right now, I've got calcium and I've got lead. I don't want to have beryllium confusing matters because beryllium will precipitate with hydroxide. Say I use hydroxide later on. I don't want beryllium messing up my results, right? If I add beryllium and I'm trying to get calcium, I'm going to have it's going to contaminate the results. I'll get both of those precipitating. I want something that will not precipitate with anything I'm going to add in the next step. So who will never precipitate with anything? Hydrogen ions, ammonium ions, and alkali ions. Now, hydrogen I would not choose because it is acidic. And therefore, you might end up with an acid-base reaction that you don't want. Ammonium is also an acid, so I don't want to add it because I could end up with a reaction I don't want. So who am I left with? Alkali ions. And of those alkali ions, there are 3 that are reasonable choices, and there are 3 that are somewhat silly choices. Who are the silly choices? Silly choices are... Like in terms of, I would like you to go to the back room and find me a jar of blah. Which ones are you most likely to find? Na plus is the most likely, maybe K plus. So this is your best choice. This is your second best choice. This is kind of your third best choice. Do you think you're going to find rubidium chloride or rubidium sulfide in our back room there? No, because they are they're much rarer elements. Okay, so you want something that's going to be easy to find. So if you wanted to add chloride, you would add sodium chloride. Whoops. Sorry, I keep going to the wrong page. So we could add lithium, potassium, sodium, rubidium, cesium, francium. But these ones are rare, so we're going to say no. These ones are good, and I would say sodium is probably the best because it's so common, okay? So what's the formula of the compound that we are going to add? Tell your partner, what's the formula of the compound we're going to add? We're wanting to add chloride ion, and we're partnering it up with sodium, so we are adding NaCl. And the next question is, how much of this compound do we need to add? Well, the deal is that we want to precipitate out all of the lead. Because otherwise, if there is lead hanging about, it will complicate our next step. So we want to get rid of all of the lead. So we need to add an excess, and the word excess means more than enough. So we need to add more than enough NaCl to precipitate all the lead. Now, don't worry about how much that's going to be. This is a qualitative, just sort of, these are descriptive questions, so we'll worry about amounts, later on, okay? Now, if you add this to the beaker and you're like, okay, here's my beaker, and maybe there's some calcium in there, and maybe there's some lead in there. If we add in NaCl, now we have chloride ion. What are we going to see if there was lead?
Precipitate.
We will see a precipitate. Do you guys know what a precipitate looks like?
Yes.
It looks cloudy. Precipitate looks cloudy. Sometimes even opaque. Okay? So if we get a precipitate, did we have lead? Yes, because this would make a precipitate. What if no precipitate forms? What if it stays clear and colorless? No lead. So you make a statement. So this is like step 4 of the process. You make the statement and you say, if a precipitate forms, yes, lead. If you get a precipitate, there was lead. If you get no precipitate, there was no lead. Or you can say lead wasn't present. Okay? Yay! Now we know that lead was present or not present. Now, if it was not present, we can just move on to the next step because we have, if no lead, go to next step because you have a clear colorless solution. But if there was lead, our solution is like all cloudy. And we're like, do I have calcium? if I add something to turn the calcium solid, if I precipitate the calcium while there's this lead chloride is still hanging about, will I know if I actually have calcium? No, because I'm like, did it get more cloudy? Or is it the same cloudiness? I just can't tell. So if there was lead, and we have PbCl2 solid, we need to remove the lead chloride somehow. If there was lead, we must remove the lead chloride solid somehow. So I would like you to think for a moment and see if you can think of a way of removing the lead chloride. And in the meantime, I'm actually going to go get some lead and some chloride so you can see what a solution. Actually, I'll get lead and iodide because that's more exciting.
That's great.
To be fair, that was my first issue. Oh, that thing. Spin
Okay. So this is not some random lead solution. This is lead nitrate. Okay. This is 0.01 molar. And I'm using a very low concentration of lead because lead is toxic and I don't want to generate very much waste. Okay, but it does produce a spectacular reaction, which most others don't. Usually they kind of produce a sort of fluffy white precipitate, which is not nearly as visually stunning as this one. So here we have some potassium iodide. This is 0.1 molar. The lead nitrate, 0.01 molar. So I'm making sure that I have how much Ki compared to lead. So the lead is 0.01, and the iodide is 0.1. Which one is in excess? Okay, the I is in excess because I want to precipitate all of the lead. Now, if we look at these, what can you say about these?
They are colorless.
They are colorless. They are clear. Yes, they are clear, colorless solutions. Now, if you blink, you're going to miss it because this is a double replacement reaction. What do you know about the speed of double replacement reactions? They are fast. Okay, so are you ready? 5, 4, 3, 2.
Wow.
Whoa, what did we get?
Yellow, cloudy solution.
We got a yellow precipitate, okay? And it's so cloudy that it is actually opaque. Light will not pass through this solution very well, okay? Right? All right. Now, there is solid floating around in there. That's what makes it cloudy. How can I separate out that solid from the liquid?
With a filter, maybe.
I could filter it. Filtering with a volume like this, it's very small. Okay, so if I had a larger volume, filtering would be a really good choice. Okay, but I have a very small volume. Probably if I poured this through filter paper, most of the liquid would just kind of get absorbed by the filter paper and then evaporate. So what would another choice be? That thing. Do you guys know what this is? Anyone seen this before?
Oh, yeah, you.
It's a spinny thing. It's called a centrifuge, and we're going to watch just very quickly a little video on a centrifuge because then you'll see it like actually moving because it's really hard to see the inside. Okay, we're going to watch a couple of videos actually. Here we go. Doo-doo. Keyboard. There we are. Centrifuge video. Okay, we're going to go to this one because it just shows you how to use a centrifuge. Actually, do I even want to do that? But it linked me to the other one. So we're going to go here for just
Most
a
people
second.
have no clue that in
Yeah, blah, blah, blah. Okay, we don't want that one. We want this one.
When a liquid containing suspended materials is allowed.
I have ad block. So on your computer, ad block blocks ads on YouTube, but it does not do it on your phone, and it does not do it on my TV either, which makes me sad. But it works nicely on the computer. So. Okay, so the reason we're watching this is because it's really hard to watch what's going on inside here without every single person coming and like standing over it, and we don't have enough centrifuges to do that. So this one actually takes all the outside part away and it just shows you what's going on kind of inside. So here's this guy.
Allowed to stand for some time, the heavier particles will settle down through a process called sedimentation. This can be used to separate the material from the liquid. But what will we do if the suspended material is very light? It will take days to settle. In such cases, we can use the process of centrifugation to quicken the process of sedimentation. Centrifugation is the process of separating substances of different densities from a mixture with the help of a centrifuge. Let us conduct an experiment to see centrifugation. For this, we need a handy centrifuge machine, muddy water, mixture of calcium carbonate in water, 4 centrifuge test tubes. Take the sample of muddy water and place the test tubes in the centrifuge machine.
And it's important that the two levels of liquid be equal.
Now
We'll
take
talk
the
about
calcium
why
hydroxide
later.
mixture in the test tubes and also place them in the centrifuge machine. Rotate the machines fast for few minutes.
So that's what's happening inside here, essentially.
Stop rotating. Remove the test tubes and observe. We see mud particles and white precipitate have settled in each of the test tubes. This is the process of centrifugation. In a centrifuge, as we rotate, the substances experience centrifugal force away from the center, which forces the materials against the wall of the tube. The amount of centrifugal force experienced by any object depends on its mass and the speed of rotation. The components of a mixture get separated because the denser particles are forced to the bottom while the lighter ones stay at the top. So with an increase in the speed of rotation, even lighter materials can settle down. Centrifugation is used in diagnostic labs for blood and urine tests. It is used in dairies and homes to separate butter from cream.
Okay, now we are going to centrifuge this sample that I just put in here. But before I do, I need to make sure that I balance the two sides Because if I don't, what did I do with the other test tube? Oh, I put it in here. Okay, that's not the same test tube. Oh, that's okay. I need to make sure that the level is the same because does anyone have a top-loading washing machine? One where you put the clothes in the top?
Yes.
Yes? Okay. Used to be that I could do this for everyone. Everyone would know what I was talking about. I have a front-loading washing machine, or sorry, a top-loading washing machine. And let's say that you've got like a heavy woolen sweater or something and it's in there. The whole thing spins, and if you've got too much on one side and not enough on the other, what it will start to do is it'll start to go, and it will actually move across the room and like twist and like try and escape. Yes, so when you hear that noise, you're like, ah! And you have to go turn it off and redistribute the load so that it is equal. A similar thing will happen here because it spins much faster than your laundry. So we want to make sure that the amount of liquid is similar so that it is balanced. Okay, that's pretty good. So I'm going to put these opposite one another. That's the other thing. Oh, there's my other test tube. I put it in there. Ha, that was clever of me. At any rate, you want to make sure that they're right across from each other and not like one here and one here, because if you put them both on one side, what's going to happen? Okay? Yes. And now we're going to turn this on. And then we wait. So while we wait, we can go over here and we can learn about what we're going to do after we've spun it. So there's two parts to this. Right now we are doing the centrifuge part. And afterwards we are going to do the decant part. The supernatant super is a prefix meaning above. The supernatant is the liquid. And I'm going to turn this off. It makes a very satisfying ding noise. So just, I always find that very relaxing, that little ding. I'm like, oh. All right. And they always say not to lift the lid until it has finished spinning. I'm always way too impatient to do that. So just once it's slowed down a little bit, this one's not super, super fast, so I'm not going to rip off my skin doing that. Okay, and what has happened is that some of it has stayed on the side, but most of it has gone to this other side. And I'm going to use that other test tube that I had actually to do the decanting part. So I have the supernatant, which is the liquid part, and then I have the solid part stuck to the wall, which is called the pellet. The pellet is the solid, supernatant is the liquid. And now I'm going to decant, which simply means to pour the liquid off and leave the solid behind. Okay, now you can see there's still some of the solid in there. Shall we centrifuge it again and see if we can get more of a separation?
Yes.
Right? Because you can see it's still a little bit cloudy, it's still a little bit yellow. Let's see if we can't separate it a little bit better. We'll maybe run it a little bit longer this time. So while we're doing that, our supernatant is the liquid, the pellet is the solid. And what we're showing in the next step is the solid down below, the liquid up above. And if we have a large container, we would use a glass stirring rod. The reason we use a glass stirring rod is it prevents splashing. So the reason we use a glass stirring rod is that water is a polar substance, yes?
Yeah.
Glass also has little polar bits on it. So if you pour it, the water will flow down the glass stirring rod rather than just sort of splashing randomly anywhere, okay? And so you can direct the flow of your pouring much better. It also prevents, you know how sometimes when you go to pour something, instead of pouring nicely, it'll like go down the edge of the pouring thing. Well, this prevents that because it'll be like, oh, I'm happy to go to the glass stirring rod rather than go down the glass on the outside. So it's kind of a nice little technique there. And that's our, oh, we're getting there. Okay, let's see. Not bad, hey? I think if we ran it for longer, we could get out even more, okay? But we're done now, okay? You get the general idea. So that process involves two steps, the centrifuging and the, what do we call it when we pour the liquid off? Decanting. Your other option is to filter. This works better for bigger volumes. And to be honest, waiting for something to filter is really boring. Okay, the centrifuge, you have to wait a little while, but not as long as you have to wait for filtering. So in real life, if you had to choose between centrifuging and decanting and filtering, most of the time I would choose the centrifuge and the decant. If I'm writing an answer to a problem, filter is a lot shorter than centrifuge and decant. So I might choose filter in that particular instance, okay? But whichever you prefer. I've always been a centrifuge and decant girl. I don't know why. It's how I learned it first in grade 12 myself back in 1989. Well before the turn of the century. I don't feel old at all. Okay. So here's what we would do if we filter it. We've got our filter paper. We've got a funnel. The liquid comes drip, drip, drip. We don't call it a supernatant anymore because super means above, and it's not above anything, is it? It has been filtered, therefore it is called the filtrate. You are not responsible for knowing the terms supernatant and filtrate. I'm just letting you know because if you go off to university and take a lab course, it will be nice to have heard the words before, okay? You are not responsible for supernatant and filtrate. The solid is called the residue. It's no longer called the pellet because it is not a pellet anymore. It's not sort of jammed into one corner. It's all spread out all over the filter paper. Okay, so now we have a clear solution, just like that, okay? And we're like, oh, I wonder if there is calcium in there. Do you remember our first solution? Would we ever have been able to tell if we had calcium, if we precipitated something with that bright yellow whatever? We wouldn't have been able to. So now we can look at this and say, do I have calcium? Can you please find something that would precipitate the calcium?
Sulfate.
Sulfate is a good choice. Is there anything else that would work? Yep. Calcium would work with sulfate. Calcium would work with hydroxide because it belongs to the all others category. And that would be low solubility. And calcium would also fall in the low solubility category along with sulfite, carbonate, and phosphate. So any of those are good choices. So who could we use? We could use sulfate, SO4. We could use hydroxide, carbonate, phosphate, or sulfate. So if I were writing my next step, what would I have to say? You're going to critique this. Let me know what you think about this as your next step.
No.
Would you get full credit for that?
No.
No. There's two things that are wrong with it.
Positive ion to go with it.
I need a positive ion to go with it. Who is a good choice of a positive ion?
Alkali ions.
Alkali ions, and in particular, my very favorite is Na+. So we're not going to add sulfate. We're going to add Na2SO4.
Should you put a detail that you add that to get all of it?
To be honest, because this is our last step, you don't have to, but I'm going to get you to do it anyway, just so you get in the habit of writing add and excess. Do you know what I mean? So we're not just going to add some, we're going to add an excess of Na2SO4. After we add an excess of Na2SO4, we need to look at our results. What might we see? What are the two possibilities that we could see? I've got this beaker. I add some Na2SO4. Maybe there's calcium in that beaker. Maybe there isn't. What are the two options that I could see? I could see clear, or I could see cloudy, precipitate. So we either have a precipitate or we have no precipitate. So what have I done? If precipitate Ca2 plus, was it present or not present? Was present. If no precipitate, no Ca2 plus was present. So, are we good with that? Making sense? Okay. At this point, it doesn't matter if the ion would also precipitate lead, because the lead has all been removed. Now, do you remember back here when we added sodium chloride? What if instead I had added beryllium chloride? Or magnesium chloride? Let's go see what would happen with sulfate.
It would be soluble.
Oh, I chose the two that are soluble. Silly me. What if I had chosen barium sulfate? Or barium chloride, actually, barium chloride. It would mess it up, yes? Where did it go? There we are. So beryllium chloride would have been okay, magnesium chloride would have been okay, but barium chloride would not be okay. Do you want to muck around deciding which one of these might be okay or not? Or would you rather always choose sodium chloride, which will never mess things up? Sodium will never mess things up, ever.
Always choose sodium.
Always choose sodium, okay? Or potassium, but sodium's sodium's the best go-to. Shall we try the next example?
Yes.
Okay. And we're going to actually do this one together because it gets a little complicated. Okay. We have either phosphate or sulfate or both. So I would like you to go and see if you can find an ion that will precipitate only phosphate or only sulfate, but not both. It's a little trickier for this one. See if you can do it.
So this one is AGCA. Okay.
Sarah, wake up. Find us an ion that will precipitate sulfate or phosphate, but not both, if you can. This one's trickier. Or you can just go back to sleep.
Wait, what? I'm confused. Okay, okay. It's these two, right? So I would say, oh, you can just use this. And then this one also just use the name. Wait, so how about we just do, how about we classify, how about what's it?
Sulfate and phosphate. We want to separate sulfate and phosphate.
Phosphate, we'll just use all the, we'll just not use the soluble ones and the ones that are soluble for the sulfate. No, because wouldn't that also make it acidic as well? Look, there you go, chemist.
You've been chemistrying.
I have a chemistry.
Okay, my first question to you is, what about these ones here? Silver, calcium, strontium, barium, lead. Can we choose those?
No.
Why not? They'll precipitate sulfate,
They will also precipitate phosphate.
but they will also precipitate phosphate because they belong in the all other category. So we've got Ag plus, Ca2 plus, Sr2 plus, Ba2 plus, and Pb2 plus. So the only thing we can say about at this point from that data is it's going to not be these ones. Are there any other ions that are not a good choice?
Alkali ions, H ions, and H4 ions.
So all of our alkali ions, the H plus and the NH4, are up in the all others. They are soluble for both, right? Because these include alkali, H plus, and NH4. So silver, calcium, strontium, etc. will precipitate both. All your alkali ions, so that would be like sodium, potassium, lithium, would precipitate neither. So what are you left with? Everything else. So seriously, you can go to your periodic table and be like, let's pick something. We cannot use the alkalis. We cannot use silver or calcium or what were the other ones? Silver, calcium, strontium, barium, lead. Silver, calcium, barium, strontium, lead. What are we left with? Everything else. Do you think it would be a good choice to use iridium?
No.
No, because that's weird. Pick something like you've heard of. Okay. Magnesium is a good choice. Copper, zinc, iron, right? Something you've heard of that like just is not going to be terribly difficult. So you could pick any of those. I'm going to go with magnesium because it's a fairly straightforward choice. But literally, if you chose to choose zirconium, you could do that. It's just a little weird, okay? Technetium, molybdenum.
Not valid because it will also put the, possibly count down. This is a no. And
So, last time we needed to pair up our anion with a cation. This time we need to pair up our cation with an anion. Who would be a good unreactive partner?
sulfide. Yeah. And nitrate. Actually, yeah, nitrate must be wrong with it.
I would say rather than going with sulfide, which looks a little dodgy to me, I'd have to think about sulfide, right?
Yeah.
Like I'd have to put some mental effort into that. Who do I have to put no mental effort in?
Nitrate and acetate.
Nitrate and acetate. And I'm going to say go with nitrate because acetate is what?
Organic or alcohol. What about it? No, sorry. No, acid and organic. No. Oh, it's base.
It's a Bronsted-Lowry base, okay? Because it can gain a proton and become CH3COOH. So in general, just go with nitrate, okay? Nitrate, good choice. So go with sodium for the positive one, go with nitrate for the negative one. We're going to choose magnesium here. The best unreactive anion is always nitrate, NO3 minus. So now we need to add an excess of, tell your partner who.
NO3 minus.
Are we happy with that?
No, Mg NO3
I thought that's what you meant. Okay, we need to have our cation in there. Okay, so we want the Mg, we have to pair it with something, so we've paired it with NO3.
Mg NO3.
Then we make our statement. If a precipitate forms, then we have to go back and say, who did that precipitate? That precipitated, did it precipitate the phosphate or the sulfate? And if you forget, you can go back and you can say, who did it precipitate? Magnesium precipitated. Magnesium would be up here. Magnesium would be down here. So it precipitated the phosphate. Why do I keep going to the wrong screen? If no precipitate forms, no phosphate was present. What do you need to do next? Tell your partner. So, whoa.
We need to do that. We need concentric and decant.
To the remaining solution, because you got to tell me what you're adding it to. Are you adding it to the precipitate or are you adding it to the solution? To the remaining solution, what would you add now? Tell your partner. Go find something. So we have no more phosphate. Yes, of course.
I would like to have a solution.
All right, what do you guys think? Who do we like? Because we want to get rid of sulfate now. We want to see if sulfate is there.
We want to add
Now we want to say, oh, I don't want no silver or calcium or strontium or barium or lead. I want any of these ones. Yes, because now we want to form a solid. So shall we choose silver? Because it's easy. It's the first one there. Okay. So what's the next word? To the remaining of solution. Add. How much? An excess of Ag plus.
of AgNO3.
Of AgNO3. Okay, we cannot just add Ag plus by itself. After you've done that, you look at your beaker and you say,
Is there any precipitate?
is there a precipitate? If a precipitate forms, SO4 2- was present. And then I get really lazy because I don't want to write the same sentence over again. If no precipitate forms, SO4 was not present. Is good? Your homework is page 20. You will need to do it on separate paper. Okay? Now, there's one thing I need to point out to you about question number 2. What does it say that is different? Question number 2 says it contains all of the following ions. Will you need to say if a precipitate forms? Or will you be guaranteed that a precipitate forms? A precipitate will form, you're just separating the ions. You're not finding out if they're there, you're just separating them one from the other. Okay? Page 20 is your homework.
I know.
Yeah, and that, no, and that's.
Hi, did you finish okay?
Yeah.
Awesome.
And then what happened was that, oh, okay, you know what's that on this time? Yeah, we're hanging with that.
Oh, okay.
And then, the next one.